Welcome to our solar photovoltaics course. Now today we will discuss about the perovskite morphology optimization. Now we have seen that one of the important parameter for tuning the high efficiency in a perovskite solar cell is not only the charge carrier generation, but how the charge carrier transport or how they diffuse along the active layer. Now very often this property, how the charge carrier transport through the diffusion layer or through the active layer, that depends upon the morphology of the devices. So that is why the changing morphology changes the grain size, changes the charge transport properties and the photophysics significantly. So today we will discuss about the different technology for the morphology optimizations in the perovskite solar cell and how they can lead to the different kind of photophysics in these devices. Hybrid organic inorganic halide perovskite have been extensively studied due to their remarkable optical and electronic features, as high absorption coefficient, long exciton diffusion length, excellent carrier transport and low exciton binding energy, as well as a facile solution process for the fabrication of organic inorganic halide perovskite. High efficiency solar cells with methyl ammonium lead halide perovskites have been successfully achieved within just a few years. The high quality perovskite films have made a significant impact on the fabrication of efficient and stable hybrid perovskite solar cell. Now morphology engineering has been recognized as an effective way to obtain highly crystalline and pinhole free perovskite film with optimum grain size. Here primary techniques related to morphology engineering are discussed, introducing additive engineering, solvent engineering, humidity control, compositional engineering, thermal engineering, self assembled monolayer and interface engineering. Let us look at this chart. So the classification of the morphology engineering can be manifolds. It can be additive engineering, that means while fabricating the active layer we can put an external additive as a solvent. We can use humidity engineering, that means if we control the humidity or if we change the humidity, that affects the morphology significantly. Then we can do solvent engineering, that means if we change the solvent. So like for example, if we change from DMF to DMSO to NMP to toluene, so basically what we are changing is the dielectric constant. If the dielectric constant is different, then the polarity is also different. If the polarity is different, the way the perovskite crystallize, that also different. So the morphology also becomes different, that is called solvent engineering. Then the compositional mapping or compositional engineering. So in the perovskite we know there is an cationic group and there is an anionic group. Now we can change a single cation to 2 or 3 cation, and instead of a single anion we can use 2 or 3 anions, and when we make a combination of all of these cation and anion, that is called combinational approach or combinational engineering. Then there are interface engineering. So perovskite forms a very important layer at its interface or charge transport interface. For example, if I take a CH3NH3 lead iodide, now for an PIN geometry we use P dot PSS as a hole transport layer and PCBM as an electron transport layer. Now the perovskite P dot PSS interface and perovskite PCBM interface is very important while designing an efficient solar cell. Instead of PCBM, if we use some other electron acceptor layer, or instead of PCBM, let us say in addition to PCBM we use BCP as a small molecule, or if we evaporate the C60, then the morphology will be completely different. Then thermal engineering. So what temperature we anneal the perovskite, like after making perovskite film with this precursor solution, then usually we anneal the film. So annealing means heating the film at a particular temperature. Now usually we heat it at 120 degrees Celsius. Now if we heat at 150 degrees Celsius, or if we heat at 100 degrees Celsius, or if we heat at 90 degrees Celsius, the resultant crystallinity, packing and morphology will be way different. That is called morphological optimization. And then the self assembled monolayers. So how we make the films? We can make the films by one step approach, we can make the film by two step approach, we can do a self assembly. So these also change the packing or the crystallinity of the film. So that also change the morphology of the perovskite film. So these are all different technology for the morphology optimization, and what it changes? It changes the efficiency as well as the stability, the two important parameters in a perovskite solar cell. Now let us look one by one factors. First is the additive engineering. Various kind of additives have been doped into the perovskite layer as an effective way to enhance the surface morphology in a hybrid perovskite solar cell. For example, inorganic salts, organic halide salts, inorganic acids, fullerenes, polymers and even water. In general, the crystallinity of hybrid perovskites is enhanced by doping additives into the perovskite layer so that highly purified and smooth perovskite layers can be formed. leading to highly efficient and more stable hybrid perovskite solar cells. Cao et al. Applied a series of organic halide salts with different organic cations and halide anions as processing additives. They found that TPPI, tetraphenyl phosphorylium iodide, and chloride are the most efficient additives for an improvement in the crystallinity and morphology of the hybrid perovskite film. For example, if we use a different additives, like with the perovskite, only perovskite, this is the SCM image. If we use 1% TPPI, so the morphology improves. If we use 1% TPPCl, the morphology further changes. So, what we mean by changing the morphology is the smoothness, uniformity, crystallinity and the packing, and these all affects the charge transport properties. So, there are different approach by just, for example, Liu et al. Have shown that perovskite film quality can be improved by adding methyl ammonium solution based additive, considering reducing intrinsic defect density in a thick polycrystalline layer. As a result, the extended carrier diffusion length and heterojunction planar solar cells are fabricated with a 650 nanometer thickness layer, and that can give an efficiency of 20.02%. By using hydrogen iodide HI as an additive, smoother perovskite layer can be fabricated through an intermolecular exchange process, resulting in a decrease in the deep level defects, and the defect engineered thin perovskite layers enable the fabrication of perovskite solar cells with a higher PC efficiency. Similarly, the self-assembled monolayers were firstly applied to the field of synthetic sophistication. Self-assembly leading to a supermolecular organic silane layer can improve the surface morphology of hybrid perovskite. Hierarchical organizations of interlocking components provides very complex systems. The ability to combine the head and tail group of constituent molecules makes self-assembled monolayers as effective method for surface modification. Well, for a self-assembled monolayers, we do a silane chemistry. So, you use silane molecule. Now, these are like amphipolar. So, it has an hydrophobic group, it is an hydrophilic group. So, now the way the hydrophobic or hydrophilic group they assemble on the perovskite layer, that change the way of the packing or the crystallinity. Although the exact mechanism of the SMs have remained ambiguous until now, it is still an attractive approach in the field of perovskite solar cell. The power efficiency of the hybrid perovskite solar cell can also be enhanced by introducing silanes as self-assembled monolayers between titanium oxide and the perovskite layer. The resultant SEM and FTIR measurements showed that an organic silane layer can improve the surface morphology of the hybrid perovskite by incorporating SMs between TiO2 and CH3NH3 lead iodide, and printable HPSCs have reached an efficiency of 12.7% in the large area devices. Huang and his co-worker reported that a stable perovskite solar cell device can offer an efficiency of 19.5% with a fill factor of 80.6% by the introduction of cross-linkable silane molecule with hydrophobic functionalization and doped fullerene as an electron transport layer as shown in the next figure. So, you see here like between the transparent conductive oxide we put a whole transport layer, and then there is a perovskite, and then there is a doped ClCs layer, and then we put the electrode layer. So, here we are showing an example of a silane, like if we put a cross-linkable silane bonding which has a hydrophobic tail which is protruding towards outside. So, that is make a hydrogen bond with the transport layer, and that increase the stability and the efficiency of the perovskite solar cell. Another important techniques in the morphology optimization is the thermal engineering. Hybrid perovskite films can generally formed by heat treatments to get rid of residual solvents in the solution based process. Produce the perovskite films is precursor and improve crystallizations and enhance the grain growth. For hybrid to inorganic organic perovskite, it typically takes a sufficient annealing time to achieve full conversion. During the annealing process, the quality of the hybrid perovskite film depends on several significant factors such as the film thickness, the heating duration, the temperature and the film composition. So, for example, if I take two perovskite precursor CH3NH3 iodide and lead iodide, and if we mix them two to get a CH3NH3 lead iodide, okay. So, it depends upon at what temperature we have sintered this film. As I said that if the temperature changes from 100 to 120 degree centigrade or 150 degree Celsius, the resultant morphology of this film will be completely different. Similarly, how long we have heated the film? Have we heated the film for 10 minutes or 5 minutes? That will also change the morphology. And also what is the ratio, whether we have used a less lead iodide or where we have used a further less iodide, or whether we have used an excess lead iodide, that also change the morphology. So, all these parameters affect the morphology of the perovskite film. Now, there are several groups which are working on the thermal engineering. For example, these Eparon groups, they have systematically studied the influence of thermal annealing on the morphology control of the hybrid perovskite film. They found that perovskite layer could be seriously damaged by prolonged heat treatment at high temperature owing to the decrease in surface coverage. So, for example, if you expose the perovskite film at a very high temperature for quite a long time, the film will damage. Additionally, the higher thickness of the hybrid perovskite film would play an important role in the coverage of hybrid perovskite as well as in the performance of the solar cell devices. Thus, the development of new annealing process to obtain thick and continuous perovskite layer at low temperature become a promising photovoltaic technology. If we wanted to make perovskite solar cell on a roll-to-roll transparent substrate, then we have to make it at a low temperature, because we cannot process the perovskite at high temperature in a transparent substrate. Here we are showing that for 3 different perovskite composition, for example, MaPbI3 and MaPbI3 is to FaPbI3 1:1 ratio, and for FaPbI3 one is the methyl ammonium, another is the formyladium, and in both cases we are using iodine. So, if we change the temperature from 100 degree to 175 degree to 230 degree Celsius, what will happen to the film morphology? You can see that when we go from the 100 to 175 degree, the grains become larger, but at the same time the continuity becomes, the film gets suffered. Similarly, when we go to the 230 degree Celsius, the film started degrading. Now, instead of the only MaPbI3, if we use a compositions of the Ma and Fa group, then the morphology is much better. You can see a well defined grain with a distinct grain boundary. If we change the temperature, this grain become larger, which is the required thing which we need. But if we change to further temperature, then irregularity comes or the surface roughness will increase. In the last figure, we are showing the FaPbI3, the formyladium based only lead iodide things. Here the morphology is not as good as the MaPbI3 or not as good as the compositional mapping, but still we get a larger grain size as we increase the temperature. In the lower graph, we are showing that systematically if we change the temperature from 100 degree to 290 degree Celsius, how the grains will be different for MaPbI3 as well as for FaPbI3. So, the temperature dependence of the formyladium lead iodide, methylium lead iodide and their mixture has been investigated in details. And the last figure that shows that SMUH of the hybrid perovskite compositions at various annealing temperature. The best coverage of the lead perovskite, for example, MaPbI3 films were achieved at 100 degree Celsius, while the coverage at 175 degree was not good like for 100 degree Celsius, and the MaPbI3 at 230 degree Celsius decomposed to lead iodide. The mixture at all annealing temperature shows good coverage. The crystal of lead iodide along with the Fa cation, so that is FaPbI3 perovskite films are hardly observable at 100 degree Celsius, while the FaPbI3 crystallize at 175 degree Celsius and 230 degree Celsius can undoubtedly be recognized. So, once we go to Ma to Fa, the change of the temperature effect is very visible. For the MaPbI3 100 degree Celsius we get a continuous film. Once we go to the 150 degree Celsius or 175 degree Celsius, the grains become larger, but it also started degrading. If we go to high temperature like 230 degree Celsius, it degrades to lead iodide. But for the case of the Fa based perovskite FaPbI3, we get a better uniformity, coverage and the grain size in the case of 175 degree Celsius. And if we go to 230 degree centigrade, the change is also very obvious. So, as shown in the figure, the MaPbI3 perovskite showed a dark color at 200 degree centigrade, and at 230 degree centigrade the perovskite started decomposing. Furthermore, the Fa based perovskite had a dark color up to 260 degree Celsius, and there after that they started decomposition. So, basically the Fa based perovskite has a better thermal stability than the Ma based perovskite. So, as a result, the optimized annealing temperature for a mixture of the Fa and Ma based perovskite is at 175 degree centigrade, where you get a uniform coating and also a very uniform grain size. Now, what about the interface engineering? The interface plays a crucial role in photovoltaic devices. The high performance of solar cell can be parsed by controlling the carrier behavior across the relevant interface. So, the high performance of solar cells can be pursued by controlling the carrier behavior across the relative interface. The long term stability of solar device can also be achieved by retarding interface aging. As a result, rapid progress related to the interface engineering has been made by managing the carrier dynamics at the interface and designing a rational structure to improve the performance and stability of the devices. The stability of photovoltaic devices has been widely addressed by interface engineering. Planar heterojunction hybrid perovskite solar cells are mostly degraded due to the interface decay of perovskite cathode. When HPHC were exposed to air, numerous bubbles were produced instantly at the interface and then those bubbles grew. After 1 hour exposure to the air, the efficiency of the solar cell device was completely lost owing to the peeling of the cathode electrode from the device. So, if we expose it to the more and more humidity or more and more water vapor, so the cathode layer will started peeling up from the interfacial layer. Interface modification of the hybrid perovskite solar cell can be realized by the interlay or the so called buffer layer, electron buffer layer EBL and the hole buffer layer HBL, which are deposited either above or below the perovskite layer in order to modify the energy level alignment and to improve the surface morphology. Various kinds of interface modification layers are applied to enable better contact between hybrid perovskite and ETL or HTL and to increase the efficiency of the electron and hole transport. For example, here we are showing the interface engineering. You can see that on the ITO substrate we put a hole blocking layer and an electron transport layer, and then we put a perovskite layer, and in the top we have an electron blocking layer and then the hole transport layer. Cesium bromide was also used as an efficient interfacial modification layer between the electron collection layer and the CH3NH3 lead iodide chlorine absorber layer to enhance the performance of the planar heterojunction perovskite solar cell. In addition to the solar cell device, the CSBR interface modification showed improved stability under the UV light and due to the decreased chemical activity and reduced defect density at the CTiO2 perovskite interface. So, if you use cesium bromide as an interfacial layer, so not only the efficiency increase, but the stability also increase now because the UV degradation now got reduced. For example, here we are showing the only TiO2 layer and the TiO2 layer in the presence of the cesium bromide. So, this y axis is the intensity and the x axis is the binding energy, and also it has been shown that when we use the TiO2 and this kind of solar cell, so the CSBR will be energetically favorable or the energetics will match in this kind of devices. Now, another important approach is the compositional engineering. The general formulas of the 3-dimensional organic inorganic halide perovskite is ABX3, where A is the monovalent cation such as methyl ammonium, formaldehyd or cesium, B is the divalent metal cation such as lead, cadmium, tin, palladium or manganese, and X is a halide anion. An important aspect that makes halide perovskite successful is the adaptability of the structure type towards A, B and X size distribution, which allows for tailoring of the properties to meet particular requirements. A central principle in the development of hybrid organic inorganic perovskite is the Goldschmidt tolerance factor, which can evaluate the ionic size mismatch which the perovskite structure will tolerate until a defined structure type is formed. So, in the ABX3 crystal structure we can change either the A site, we can change the B site, we can change the X site. If we change either of them or is any one of these three, so not only the band gap changes, but the morphology also changes. But one has to make sure that the tolerance factor, the value of T, which is basically the radius of the Ra cation plus the radius of the X divided by square root of Rb plus Rx, that value we need to calculate once we make these changes. And if the tolerance factor value is between 0.9 to 1, then it is a cubic structure. If it is between 0.7 to 0.9, then it is a tetragonal or orthorhombic structure. If it is less than 0.7 or greater than 1, then it is a non-perovskite structure. So, to have a perovskite structure, we have to have the tolerance factor value between 0.7 and less than 1. So, it should be between 0.7 and 1. If it is 0.7 to 0.9, then it is an orthorhombic or tetragonal structure. If it is 0.9 to 1, then it is a cubic structure. And T greater than 1 is a 2D layered perovskite structure. Compositional engineering is one of the most effective ways to modify the surface morphology of the hybrid perovskite for the fabrication of highly efficient and stable solar cell. For instance, like one of the research group Jion et al, they found that if we use a compositional mapping of FA and PB group, so they process the best photoelectron properties among similar kinds of hybrid perovskite with the general form of FAPBi3 1 minus x, MAPBBr3 x, delivering HPSC with an efficiency greater than 18%. They demonstrate that the incorporation of the MAPBr3 into the FAPBi3 can stabilize the perovskite phase of FAPBi3 perovskite. The A site cations, typically methyl ammonium of 3D hybrid perovskite, have recently concentrated on hybrid perovskite formaldehyd, cesium and rubidium cations. The ionic radius of the Fa cations is larger than that of Ma cations, leading to a reduced band gap of FAPBi3 compared to that of MAPBi3. In addition, compared to MA based HPSC, Fa based HPSCs have shown improved long term stability, making them more suitable for application in a single junction solar cell. So, not only the efficiency, but stability also increase in this kind of compositional mapping. Now, compositional mapping can be several fold. For here, like A, which is a can be possible of 13 protonated amines. For example, it can be NH4 plus, NH3OH plus, NH3 NH2 plus, or all of these things. As a B, we can use these 21 divalent metals M2 plus. As an X, we can use any of this. So, if we use any of the combination with any of the other combination, we can get a compositional mapping, and all of this structural combination will give us the perovskite structure. So, this chart we can use as a master's chart while fabricating the perovskite, but we have to also calculate the tolerance factor to make sure that the value of T is between 0.7 and 1, so that it is a 3D perovskite. If it is T greater than 1, then it will be a 2D perovskite. Mixed cation perovskite have become more attractive because pure perovskite material such as MaPbI3, FePbI3 and CsPbI3 come with various drawbacks. Furthermore, the combination of different cations can merge the merits of the constituents while avoiding their disadvantage in the perovskite layer. So, when we do the compositional mapping, we not only get the advantage of the single perovskite layers, but also some of the disadvantage we can eliminate. It has been shown that the enhanced photovoltaic efficiency and long term stability of the hybrid perovskite solar cell could be achieved by introducing different cations into the crystal structure of the perovskite. For example, Saliba et al. Used a mixture of triple cesium MaFa cation to fabricate hybrid perovskite solar cell, reaching a stabilized power output of 21.1% and 18% after 250 hours under operational condition. Now, over 80% of the initial efficiency of the optimized hybrid perovskite solar cell can be retained in the dark condition for 200 hours. So, basically the Tai et al. They have reported that a lead thiocyanate precursor was used to fabricate the solar cell in ambient air. The pinhole free morphology of this lead thiocyanate based perovskite solar cell can be prepared under high humidity to avoid direct carrier recombination at the HTM-TiO2 interface. And not only the stability increase in these thiocyanate based devices, but also the efficiency can also be tuned. Now, another important tuning parameter is the solvent engineering. The control of the crystallization and hence the kinetics of the film growth, that can be controlled by changing the solvent. To improve the morphology of the hybrid perovskite, various methods of solvent engineering and solvent annealing have been developed. The solvent engineering approach is an attractive way to conquer the limitation of the one step spin coating process and tends to make smoother perovskite film with reduced defect density. Solvent engineering is a class of fabrication technique that introduces a solvent to coordinate with the precursor solution in order to form precursor lead iodide solvent complex for preventing other chemical reaction in solution. A film of this precursor solvent complex is then cast and subsequently converted to the hybrid perovskite. Specia et al. Reported that uniform hybrid perovskite could be deposited by a solvent induced and fast crystallization method consisting of spin coating a CH3NH3 lead iodide precursor solution followed immediately by exposure of the wet film to chlorobenzene to induce crystallization. The chlorobenzene was dropped on top of the wet perovskite film during the spin coating process, resulting in the first crystallization of hybrid perovskite with the formation of homogeneous grains. Now, you see in this figure here, we have the CH3NH3 lead iodide in DMF solvent which we can spin coat. Now, if we spin coat in the presence of the chlorobenzene, so then what will happen, we have in the both the case if we compare the morphology, we get a larger crystallizations if we use the chlorobenzene as another solvent additive, and the efficiency also increase in this case. Now, this Zhou et al. They have employed an anti-solvent extraction method for the crystallizations of the mixed halide. So, basically while loading the perovskite in a solvent, if we add an anti-solvent, so anti-solvent means a solvent that does not mix with this precursor solvent very well. So, because of the difference in the polarity, the anti-solvent will not able to mix with the solvent. So, then they will slow down the crystallization process. As a result, we will get a larger grain size. In this strategy, a little amount of solvent diffused with the larger amount of anti-solvent. For the crystallization procedure, supersaturation state and nucleation are accomplished by the anti-solvent solvent extraction method, and the nucleation rate may be improved by magnetic steering of anti-solvent. So, you can see here the solvent extraction which is happening precursor film and the substrate, and here the accelerated solvent extraction is happening due to the magnetic steering. Another very important parameter for making solar cell is the humidity control. Hybrid perovskites are extremely sensitive towards the humidity and they are moisture sensitive. Thus, the photovoltaic performance of the solar cell rapidly degrades in moist environment due to the hygroscopic nature of methyl ammonium cations in hybrid perovskite materials. There are a series of reactions happens when you expose the CH3NH3 lead iodide to the moisture. For example, it degrades to CH3NH3 and lead iodide. Now this aqueous CH3NH3 they can further degrade to CH3NH2 and HI, hydroiodic acid, which is an aqueous solution. Now this 4HI and oxygen can react to make iodine, and this 2HI also can further disintegrate to hydrogen and iodine, its individual components. So if we keep the perovskite material under the normal humidity condition, very soon it will degrade to its constituents. In this process, CH3NH3 lead iodide could react with the water and decompose to its constituents for CH3NH3I and lead iodide. The electron injection rate could be reduced in the presence of more lead iodide byproducts, but carrier recombination lifetime could be extended upon passivation. It has been doubted that the existence of the water vapor during the film deposition process has a positive influence on film formation, because both perovskite precursor materials and lead halide perovskite exhibits some degree of solubility in water. In comparison to a film grown in dye condition, Zhou et al. Found that CH3NH3 lead iodine and chlorine mixture, that film growth under controlled humidity condition 30 plus minus 5% relative humidity exhibit improved optoelectronic properties. This is likely due to the fact that moisture could induce the reconstruction process during film formation by partial dissolutions of the reactant species and an acceleration of the mass transport within the film. For example, here you see that on the ITO we have put period PSS, perovskite, PCBM, and then BCP, and then the silver electrode we have deposited, and if we put perovskite and the DMF and the H2O, so as we increase the percentage of the water to 1% to 2% to 5%, if we look at the IV curve, the IV curves falls down. So the efficiency drops down, and even if we look at the morphology, if we expose to different water vapor, so the crystal started disintegrating. So we need to do the humidity control. Compared with the anhydrous DMF, the controllable growth of hybrid perovskite was obtained by blending suitable water additives in DMF due to the lower boiling point and higher vapor pressure of water. The surface morphology of the DMF only based perovskite film showed many small pinhole and voids. The film defects and poor surface coverage would give rise to inefficient charge transport and weak light absorption in hybrid perovskite film. If we have a lot of defects in the system, then the absorptions will get suffered. With the introduction of the water additives, the average grain size of the hybrid perovskite was increased and the voids on the surface of perovskite film surface partially dematerialized. It is noticeable that an enlarged grain size with more voids produced between the grains were found by increasing value of the H2O DMF ratio in the range 0 to 10%. As shown in the figure, the ACM result of the DMF plus 10% H2O vapor based perovskite is much more evident. The CH3NH3 lead iodine chlorine based devices, they treated with an optimum water vapor ratio of 2% exhibit a remarkable enhancement of the PSC with 16.06% with a VOC value of 0.9 volt and the JSC value of 21.61 or 67 milliampere per centimeter square and a fill factor value of 78%. So a very optimized exposure to the water with the DMF solvent sometimes helps to improve the current and the fill factor. So in conclusion, we have, despite the rapid progress in the performance of the hybrid perovskite solar cell, there are still more opportunities for the further improvement of the device. Morphology engineering has the great potential to considerably enhance the efficiency and stability of the hybrid perovskite solar cell. However, the interaction mechanism between the hybrid perovskite and other interfacial layers still remains unclear and needs to be further explored to facilitate the application of the morphology engineering. Most of the techniques of the morphology engineering have been limited to specific condition during the fabrication of hybrid perovskite films. So with regard to the next direction in the morphology engineering, film quality could be improved by either integrating these existing techniques with different function by exploring new technologies to reach distinctive and galvanized morphology controlled. In addition to the experimental approach, theoretical calculations still cannot be performed regularly in the area of morphology control, but can definitely make a significant contribute to further enhancements in the design of morphological techniques. So there are so many morphological optimization techniques are there, like solvent engineering, like thermal engineering, compositional mapping, then self assembled monolayers, etc., etc. All of these things change the grain size, all of these things change the efficiency as well as the stability, but we cannot try all sorts of combinations to see what is the maximum morphology optimization we get. So in this regards, probably some theoretical calculation or theoretical modeling help us along with the experiment to achieve a most optimized morphology and most optimized photophysics, which can lead to the higher efficiency as well as higher stability in a perovskite solar cell. Thank you so much.